Assalamualaikum warahmatullahi wabarakatuh. Hello everyone. We are from 5th group. We want to explain our project in data structure algorithm. But before that, we want to introduce ourselves. Hello, my name is Hammam Arifianto, and this is my partner.
Hello guys, so my name is Rizka, Nuha.
And my name is Tabrizzi Aqlia.
So now let's dive in.
So, major issue in hospitals is that a random walk-in patient often experience a very long waiting times because they have a lower priority compared to patients with appointment. And this study investigates whether the clinic registration system can be improved by separating the queues for these two different types of patients. Therefore, we compare two models. The first one is model P, where the queue is pulled with priority given to appointment, and model S, where the queues are separate. To implement our model, we utilize double linked list data structure in Python. We choose this structure because it's allow highly efficient data manipulation from both ends. In our mains.py script, we create a patient queue double linked list here. When it's actually a class, class. When a regular or a walk-in patients register, this function will place them in the end, or in the back, or we can say it in the tail. However, the system grants priority to appointment patients through this function. Scheduled patients will insert it directly at the very front or the head. This ensures their priority rights are made without having to iterate through and rebuild the entire queue. When it's time to service, the queue system, or this function, will simply remove the node from the front.
We already understand how the double linked list manages the queue, so let me explain how it runs in our simulations. For model P, we use two doctors sharing one priority double linked list. The simulation works in an event-driven manner, time advanced to whenever the earliest doctor becomes free. At that point, all patients who have already arrived are inserted into the double linked list based on their type, and the doctor immediately serves whoever is at the head. This continues until all patients are served. Now for model S, we use two separate first-in first-out queues, one for appointment patients, one for walk-ins, each with their own dedicated doctor. However, if a doctor's queue is empty, they can steal patient from the other queue. Now our dataset. We use a real outpatient queue dataset from Hangwu Hospital in China. We divide it into three scenarios. The first scenario is a balanced scenario. It's have equal number of appointment and walk-in patients. Scenario B is walk-in dominant with 5 times more walk-in than appointment, and scenario C is appointment dominant with 3 times more appointment than walk-ins. To evaluate which model perform better, we implement 3 metrics directly from Kwak's paper. First, pooling effect. How many more patients are served by model P compared to model S? Second, saving. How much waiting time walk-in patients save in model S? And third, loss. How much more waiting time priority patients suffer in model S?
At appointment, patients are placed ahead walk-in patient, but still follow FIFO order among the same type. And then, the model is split into two queues with a walk-stealing mechanism. The ideal doctor can take patient from the other queue. Okay, we can test from the real scenario. So we have a 3 scenarios: scan A, scan B, and scan C. I will explain from scan A. The scan A is a balanced model P. Model P is acutely more efficiently, offering waiting time only 227 versus compared with model S is 320 minutes. This pooling effect working perfectly. And then the scan B, walking majority total waiting time almost equal, but model P is most friendly to appointment patient. Only 12 minute waiting versus 38 minutes is model S. In model C, appointment majority model P still wins overall 242 minutes versus 268 minutes, but 3 is a third of walk-in patient wait longer because appointment patient take priority. Okay, this actually reflects the realistic hospital condition. So, the conclusion from the scan A, scan B, and scan C, model P is a more consistent, better across all scenario. We can see that the comparison, the model P is more better. This is not by chance because the double linked priority structure was specially designed to optimally suspension from dynamically. Okay, thank you.
So that's all guys.
See you.
See you.
Bye.